In this lecture, we link up algebraic geometry with discrete valuation rings. So we start by recalling facts from algebraic geometry. So we start with V, which is an irreducible affine smooth. So smooth means non-singular curve over, say, some algebraically closed field K. And say P is a point which lies on this curve. Now we are saying that this curve is smooth or non-singular, and what it precisely means that it is smooth or non-singular at the point P if the dimension of this space MP modulo MP square is equal to 1. Now we have talked about this space in the lectures on algebraic geometry, in particular in Zariski tangent space. So this is nothing but the dual of the Taylor's formula at a particular point P. So Taylor expansion, you modulo out the square terms and you get the tangent space. So where this MP is the unique maximal ideal in the local Noetherian ring O of P. So you have this curve V, you have taken a point P. So you have this some curve V, you have taken a point P right here. On this point P will sit our ring O of P, which you can say stock at P. So this O of P. So this will be a local Noetherian ring. And and this MP is the maximal ideal which lies within this ring, and also this maximal ideal is generated by a single element. So algebraic geometry automatically gives us that once you have a smooth curve and you take a point P on the curve, then the corresponding ring O of P which you get is a discrete valuation ring. And recall the definition of discrete valuation ring. What you need to check is that this is Noetherian, normal, and has a unique non-zero maximal ideal M. So all these things are satisfied if your point P lies on the smooth curve or on the smooth part of the curve, if the curve is non-singular. So this point P, when we talk about tangent space, it is a local condition. So therefore, even if the curve is singular somewhere here, we can always talk about the point P here. This point P will have a associated ring O of P, and this ring would be a DVR, because at least at this point this curve is smooth and singularity is right here. So if you take a ring here, then it will not be a DVR. So that is our proposition. So curve V is non-singular at a point P if and only if the stock at that point O of P is a discrete valuation ring. So this is a good way to check whether the curve is non-singular or not. So we are saying this direction is given to us via algebraic geometry. Now we want to go back in this direction, that O of P is a DVR, and that is true for every point. Then we have a non-singular curve. So suppose that O of P is a DVR. We start from here, and so it is a discrete valuation ring. Then it must have a uniformizing parameter, and the maximal ideal is generated by this uniformizing parameter. Now recall what are the elements of O of P look like. Now this is a discrete valuation ring. So the elements are of this form U pi to the n, where U is a unit and n is greater or equal to 0. And if n is greater or equal to 1, then these elements will be lying in this ideal here. Then this U pi n would lie in maximal ideal if n is greater or equal to 1. So now you can isolate all the units in this field. From OP you modulo out the maximal ideal. The residue, what you get is a field, but this will just consist of these U's units because you're taking all the pi's out. So whatever you're left with is unit. On the other hand, if you consider this elements of MP modulo MP square, these are just of the form U pi because you are killing all the higher powers. So we are just keeping n equals to 1, and powers n greater than 1, or this you can rewrite as n greater or equal to 2 because n is an integer. So all these powers would lie in the ideal generated by MP square, and you are modulo outing this thing. So the only things you are left with U pi. So there is 1-to-1 correspondence. You're taking the units in the field, and then you have U pi in this thing. So dimension of this is just 1 precisely because it is just K, and this is equal to this because you have 1-to-1 correspondence between elements like this and units here. So we have proved an important proposition of finding non-singularity at a point. So a curve V is non-singular at a point P if the associated stock with it at that point is a discrete valuation ring. So you can see this is a very important aspect of discrete valuation ring. So from here we can go to the story of divisors on a curve. So associated to every point P we have this discrete valuation V of P. So recall again how the discrete valuation ring was constructed. We basically put a valuation on some field K, and from that field K we got this so we had the field K. From field K we went to integers using our valuation, and so say K of V is our field of fractions, and so from K of V we are going to integers. So for every point P you have this O of P, which forms a discrete valuation ring which is corresponding to the valuation this V of P. So we have a valuation, say V of P here, and this will give you a DVR which is O of P. So notice that you started with this K of V, that is field of fractions, and from there you went to O of P precisely because you used the valuation V of P. Now this might all look complicated, but the simplest valuation you can think of is just counting the number of zeros or poles at a particular point. So you are given some point, say 1 on the line, and then you can count how many times x minus 1 occurs. So if it occurs as 0, you count the power of the 0. If it occurs as poles, you count this I as the pole. So simple thing which you do in complex analysis, just counting the zeros or the poles. And obviously if you change this point from 1 to 2 or 3 or 4, your valuation is also changing. So here you can think of as valuation at 1. So this is an important crutch to always keep in mind to remember how this works in a general case. So this small thing works like this. So we consider this as valuation at any function f is n, which lies in integer. So you're taking valuation of all the elements here. Now if n is greater or equal to 0, then you say that this function actually lies in the discrete valuation ring. So this ring actually lies within this, and you can say K of E is also field of fractions of O of P. So we can define divisor of f. So divisor of f is, so you have valuation of P f and at the particular point P. So this valuation is just an integer. So you have an integer. So this integer could be anything. This is just an integer. If it is greater or equal to 0, that means your function actually came from the discrete valuation ring. If it is something else like negative, then it probably came from the field. It definitely came from the field of fractions of this. And when you talk about degree of divisor of f, you just sum up all the integers. So very important fact, we have talked about this in algebraic geometry lectures. If f is a non-zero function in our fraction field of our curve, then degree of divisor of f is 0. That is, number of zeros of the function f is equal to the number of poles of f. So before we proceed further and we talk about sheaf of divisors, which comes from discrete valuation rings, so notice that from OP, if you modulo out this pi to the n, you get the spaces 1 pi pi square all the way to pi n minus 1. So that means we are considering functions in the stock whose valuation is less than n. But since they lie in O of P, it is a discrete valuation ring. So this valuation is actually lying between 0 and it is strictly less than n. Goes all the way to n minus 1. So what we are going to consider next is not modulo outing this, but actually multiplying by 1 over pi to the n. So now we talk about sheaf associated to a divisor. Now to properly understand this portion of this lecture, you have to see the playlist on Riemann Rock, in particular Riemann Rock spaces, where I have talked about divisors in much more detail. So here we are going to link these divisors to discrete valuation rings. So an arbitrary positive divisor, this is given as t is equal to this summation. We're just copying this right here. So notice how the valuation became this integer, because valuation is always an integer. This integer came right here, and now we are making this into a divisor, but we are saying n of p is greater or equal to 0 because we are taking a positive divisor. So basically this divisor lives on the stock O of p. because only then it can be this n of p can be greater or equal to 0. So first such divisor, we want to define the global sections on some open set u of v, or you can say sheaf O of t. So this gamma means global sections of O of t on some open set u of this curve v. So this is precisely those functions in k of v for all points which lie in this set u, such that f of this valuation of f at p is greater or equal to negative np. So that is the order of the pole is at most np. So order is at most np. So this we can actually understand more concretely just using discrete valuation rings. So this will make more sense when we convert this statement into discrete valuation rings. So locally you see like this, you have some open set u, so you just take points in the open set and you take product over all the points in the open set you're considering. So sometimes this open set just might consider just might have very few points. So how does it look like? So now, rather than looking at the functions and all this ring like this, you look at our discrete valuation ring, and you immediately know how our discrete valuation ring would look like. It would just have functions of this form. So obviously we have different points. At every point you will have a distinct discrete valuation ring and maybe a distinct uniformizing parameters. So we expect them to be different, or they could so they will be different. So elements look like this. So we are saying these elements here have a pole, so they have a pole. So order is at most np. This is order of pole is at most negative np, but this does not have any poles. So introduce poles of order at most n of p. So you multiply by 1 over this uniformizing parameter multiplied by n of p. So this has no poles because it is a discrete valuation ring, and the order of the pole now we have introduced is at most n of p, because this has no poles and the poles you have introduced will have order at most n of p. So it could have less than this but not more than this, because you're dividing by this, and that is what comes here. So this is a more concrete description of our global sections, and it helps to think just like this, because you can get hold of our discrete valuation ring and then you can just divide by something like this, and this will essentially give you a short exact sequence, and from there you can compute homology and cohomology. So more details on this you can see algebraic geometry by Daniel Perrin. So this is Daniel Perrin's book. He uses this to construct short exact sequences. So the name of the book I think is Algebraic Geometry. Anyway, you can Google this out. So this is it. So you can see here concretely how we were able to construct divisors on curves, and this is a sheaf because locally you can think of it in terms of stocks.